Ah, okay, you are here. Perfect. That was a missing hand sign. Okay, I will just start with the second part of the seminar. So starting with Harmonic Distortion of Drives, Issues and Solutions, Part 2. And the first chapter is Harmonic Solutions Available. So what kind of harmonic solutions are useful? That's the first question we need to ask ourselves. So first of all, I want to give you a quick overview of different harmonic solutions on the market. We have passive solutions and active solutions as two basically completely different solutions. On the passive side, we have a simple choke, which is more or less not the real harmonic solutions, more or less like the first aid to avoid harmonics. We have the passive harmonic filter in many different ways. And then we have 12 and 18 pulse transformer. These are the passive harmonic solutions on the market right now. On the other side, we have active solutions. So we have the active harmonic filter, we have active front end, and we have low harmonic drives, which I mean in this example of low harmonic drives with active input bridges. So from the topology or from the hardware setup, the active front and the low harmonic drives are typically the same. Low harmonic drive would typically have a disabled region function of the active front end. So that's the main difference between those two technologies, if any at all. Okay, so first of all, we should have a quick look at what kind of harmonic distortion can I expect on different solutions. So the first and simplest one is the line inductance, obviously depending on the value, but if we look at the 4% line inductance or DC inductance, not so big difference. We will see 35 to 45% THDI. Next step would be to add a passive harmonic filter. We can get down to 3 to 5 to 8 to 10%, somewhere in this area. Then we have active front and low harmonic drive, which are typically all designed for below 5%. Quite common is 3%, 3 to 5%. That's the values that you will reach with active front end technology. Then we have active harmonic filter, which is in this example below 5%, but basically they are scalable. So you could reach any value that you would like to. So if you need a value that maybe is only 12% or 15%, you could just scale the harmonic filter to reach this value. And that's the purpose of an active harmonic filter. So it doesn't have to be 5%. Okay, so give you a quick overview of the advantages and disadvantages of these different technologies. Looking at the first one, the simple impedance line choke or DC choke, this is obviously low cost because it's only a choke installed. It will get rid of a big part of the harmonics. So you will get, if you remember the picture from the first chapter, we will get down the harmonic distortion from above 100% down to 35, 50%, whatever kind of value you have inside the choke. But you will get rid of a big part of the harmonics. So basically, I recommend to use these kind of DC chokes, AC chokes, and for good reason, these are installed in most drives already today. Has been different in the past, but today I think most of the high quality drives have these kind of devices installed from factory, and that's good. But of course, this is not the full harmonic solution. So we are still talking about 35% THDI, which can be still quite much. So you get rid of the biggest part. That's just the first aid. And that's something you should always consider. I would never use drives without any AC or DC choke installed, unless you have very, very small power. Okay, so the next solution would be a passive harmonic filter. Basically, you can say typical performance is below 5% or below 10%. That's typical, or below 8%. That's our newest range of the third generation. you will typically get a quite good cost-performance ratio. To be fair, we need to separate. We had a seminar, I told you before, from ASIA this morning. And basically, we could see that everyone has completely different projects than we see from the rest of the world. We have a lot of buildings where they have many, many, many small drives. And in that case, you would actually not have this advantage as a good cost-performance ratio, because an active filter can be cheaper when you have a lot of small drives. I will come back to that later on. Anyway, just to mention that it is definitely recommended to have a passive harmonic filter. But first of all, you should consider the technology behind this, because not every passive harmonic filter is, first of all, a quality brand, but more important, a good topology inside. I will show you later on with some presentations, with some simulations, what is the difference between different technologies. And this can be very, very significant. The next one is the active front end LCL combination of active input and LCL. The performance will definitely be below 5%. They are quite clean in the complete spectrum. They are quite clean in the lower power area, so up to 20%, you would typically see a quite good THDI. You will have a reactive part in this area, but in the overall performance, it's quite okay. The main problem that I see with this topology is that if you don't have any region power, this technology is a little bit waste of energy, because you have the high switching device at the input. So it's not only about the installation cost of this solution that should typically be quite much more than a passive solution. It's also about the technology and that you have the high switching device. As a best guess, you can have information that when you use active front end compared to a high efficient passive harmonic filter solution with a standard drive, you have an efficiency loss of about 2%, which is quite huge if we speak about bigger powers. So from my perspective, our active harmonic filter is really much recommended when you have region power, when you have any installation where you can get energy from the grid, from the motor to the grid. That's a situation where active front end can have its benefits. Okay, so the next one would be an active harmonic filter. Looking at active harmonic filter, we get a typical performance of below 5%, but as I said, this depends on the filter size. It's fully scalable. And the advantages is that it is high performance. It's easy to retrofit in systems. You can use it for different applications. So you could make some kind of power factor correction. You could make a little bit harmonic distortion, and you can even you could solve unbalance in your system, which I don't recommend to do this way, but you could solve unbalance with these units. That's the benefit of an active filter. It's typically more expensive than passive filter, depending on the size, because you can use an active filter for many, many small drives. But yeah, that's the main thing. So you should be careful about the commissioning, because some brands you will need some very expensive commissioning, depending on where it is and how far they need to travel and where they have their next agent. So that's things to be careful about. Basically, I recommend to use active filter in combination with passive harmonic filter. So find a system where you have passive and active, or you have a system of several drives, and then try to find the best way to handle the problems. And that's not necessarily one of these solutions. That can be passive or active, but it can also be passive and active. And I think that's one of the main things that I need, or I want to explain in this seminar later on. Okay, so maybe a quick flashback if you don't know anything about active harmonic filter and how they work. The main difference in the topology is that they are located in parallel to the main setup. So they are not as the passive harmonic filter for drives, they are put in parallel. And the main passive harmonic filter is put in line with the load. So looking at this picture, a passive harmonic filter would be located around here. and the active filter can be located anywhere upstream the load, between the generator and the load. So the advantage is that you can easily retrofit it for some systems, but the disadvantage is that you will still, on this wires, you would still see the load current like this. And if these wires are long, they will have impedance and they will cause voltage distortion. So still it's good to place the active filter as close as possible to the load. But however, I wanted to explain to you the principle of the active filter. And looking at this load current, the blue one, we can see this typical camelback current waveform. So what we do is we inject harmonics from the active filter into this position, into this, this point. And that means if we add up the blue one and this whatever gold current, gold color or whatever, if we add up these two currents, we will get a clean signal because the harmonics that we inject into this are of opposite direction, 180 degrees different than the harmonics in this load current. Means they will eliminate the harmonics caused by the load. So that's the simple, or not the simple, that's the working principle of the active harmonic filter, which is, by the way, also the working principle of any noise cancelling headphones or anything that you will use, for example, from Bose or from anyone that use noise cancelling. Quite interesting technology, works more or less the same like the active harmonic filter. Okay, so let me sum up. What kind of harmonic solutions are useful? We have the inductance, which should always be mandatory from my view. We have passive harmonic filter, active front end, which is, in my opinion, not a good way to solve harmonics, at least not on simple applications where you need no DC boost, you need no region power, just simple pumps and fans. You don't need active front end technology or low harmonic drives. And we have the active harmonic filter, and we have active and passive harmonic filter working together to get the best out of two technologies. Later on, I will show you some example, or especially one example, how you can have some really, really interesting savings by using these two technologies together. Okay, so passive filter technologies. First of all, I hope you don't mind if I introduce my, or not my, but our passive harmonic filter from the REVCON range. We do this as a, you will get the same kind of filter from many different brands, from 6 at the moment, as far as I know. And this is the REVCON design filter. And this is available from 1.1 up to 280 kilowatts. We have 2 different performance levels in the latest generation. It's 5% and 8%. The typical result when you use it with a drive will be, especially if we go above 100 amp, it will be significantly better. So typical result will be 2.7, 6.7. And the main difference, especially about the 5% filter, is that the efficiency is 99.5% typically, or 99 up to 99.5. This filter is available for all voltage and all frequencies that you can imagine, at least for all voltage and frequencies in the low voltage area. So anything or any combination below 1000 amp volt is available from us, 50 and 60 hertz typically. So a lot of benefits in this technology. I will explain later on a little bit more detailed. We got the same design, the third generation of as a high power design, where we put these components, we separate the mains inductance from the filter circuits. Looking at the filter circuit, this is the main difference to other brands or to other technologies. We have a double stage harmonic filter installed. I will show you later on how other brands or other harmonic filters how they solve the problem or how they solve the THDI. It's a complete different strategy, so I think you should be aware of the difference. Okay, so a passive filter is a passive filter, right? I want to explain 4 benefits of the RHF, 5% and 8%, the passive solutions, and you can decide if all passive filters are similar. So this is the design of the RHF, the 8%, which will give you a result of 6 to 8% THDI. And this is the design of a standard 10% simple harmonic filter that you will get from quite many brands at the moment. So as you can see, the main difference is we have a double stage filter and this is a simple one stage filter. And the advantage of this is quite clear. I think you can understand that it is cheaper to produce this design than it is to produce this design. Especially if you understand that this part, this upper part, is more or less similar to this part. So we add up these parts to get a more advanced solution. So the advantage of our solution is that you will have more mitigation for more harmonics. I will show you on the next pages. To understand this, I have set up a simulation of both harmonic filter. And this simulation results in a damping diagram. So in this diagram, you can see the green one, which is the REVCON filter, a 2-stage design. These are both 10% filters, by the way. And the red one is the simple passive harmonic filter design. So to understand this diagram, first of all, we need to understand how can we understand the decibel rating on the left side. So on the left side, we can see 6 decibel is equal to 50% amplitude. That means around here, we will have 50% amplitude. So if we add a 100 amp amplitude harmonic to this frequency at this stage or here, then we will see only 50 amp left. If we add the same harmonic to 10 decibel, so for example at this frequency, then we would see 32% amplitude, means you would see from the 100 amp, you would only see 32 amp. And the next level or the next explanation is 20 decibel, and then you will always you will only see 10 amp left from a 100 amp amplitude. So that's how we can understand the decibel rating of this picture. So basically, if we are here, we can reduce up to 90% of the harmonics. And if we go down further, it gets a little bit more and more, but it's not so strong anymore. So the upper part of this picture is the most important one. Okay, so where are the harmonics on this? On the x-axis, we can see the frequencies. This is the 5th harmonic. This is the 7th harmonic, 11, 13, 17, 19. So what we do is, looking at the 5th harmonic, which is the first relevant harmonic in a 3-phase supply, this is more or less the same, no matter if you use a simple solution or a RHF solution. This is the same effect on the harmonic. On the 7th, you will see a small difference. On the 11th, you will also see a small difference. On the 13th, you will see a quite big difference, 17, 19. So all these higher order harmonics, so anything above the 7th or including the 7th and above, you will have a much stronger damping on the signals in these frequency areas. Means that for the 5th, or means that the simple passive harmonic filter focus on the 5th harmonic only, while a double stage filter gives you some kind of broadband damping across the full range. So this will solve a lot of more problems than this simple harmonic filter. And that is the main benefit of this technology. The filter will have a smooth damping across the full range and not only focus on 250 Hertz or any other 5th or 5th harmonic. Okay, so how does the other one get down to 5% THDI if they do? So I've chosen one brand which typically reach below 5%. And what they do is they typically add up an RC circuit to the single stage filter. when we do 5%, we just increase the values on this choke to get down to 5%, which works perfectly well for us. This is the main difference of these kind of two setups. So performance-wise, these solutions are more or less the same, but there is one big difference. This kind of setup is an RC circuit, and these harmonics are burned into energy or burned into heat in this setup. Means that all the higher order harmonics are just inside this RC circuit. So the disadvantage is the power loss of this system. Our disadvantage is a little bit higher cost, but we have the harmonic mitigation for all harmonics. Yeah, that's the advantage and disadvantage of these kind of things. I will show you some information about the efficiencies of these systems. I think it's quite worth to have a look at these to decide what kind of solution I want to choose. Before I move on to the efficiencies, I want to show you some background information of what you should be careful when you read it. Some kind of statement from our competitor in the end. I think the first one is quite naughty. I won't go into the details of all of them, but the first one is quite naughty. So it says performance specification in this brochure refer to 6-pulse diode rectifier with 8% DC link choke. Has any one of you ever seen a drive with a DC link choke of 8%? Please raise your hand. I would be really interesting to hear about this special drive, but I've never seen any drive with 8% DC link choke on the market. And actually it couldn't be possible because the DC voltage drop inside the drive would be so huge, they would not be able to give the performance they need. So quite a stupid performance specification from one of our competitor. I think it's quite naughty because most of the people maybe don't really understand what kind of DC link choke they have, and when they read it, they would probably expect that 8% is a typical value. So I think it's quite bad. Or other competitor refer to 0% voltage distortion. They will only get the results on the performance if you have 0% background voltage distortion, and that's physically not possible to have 0% background distortion. Yeah, just some few comments and some way where we try to educate everyone that it is dangerous just to have a filter that reach the stated performance in some kind of unique environment or some kind of simulation. So we want our filter to reach the stated performance in real life applications. We don't want to run around the world and argue why they would have, I don't know, 5.7, 6.2%. We want them to be below 5% to avoid any discussion with the customer. And that's something that you should also do because you will get involved in that discussion when you use filters with low performance. Okay, so that was from the performance point of view. Looking at the efficiency, I think there is also some really, really relevant differences. This is a diagram showing all the individual efficiencies of the RHF range, but I think to get to this picture, to give you a quick overview will be sufficient for now. So looking at, or to compare these solutions, we should look from the AC side to the DC bus. So if we look at the passive harmonic solution and compare it with active front end, we obviously have to take the rectifier and the DC choke into account as well as the harmonic solution itself, because an active front end would also go to the DC bus. So if we look at this solution, we will have power losses of at least 3%, which is, as some of you may know, quite optimistic. 3% is quite optimistic for this kind of active front end to the DC bus. If we look at an active filter and a 3-level design active filter, not all active filter has these high efficiency, we will have power loss of 1.7%, results in 98.3% efficiency. If we use a high efficient passive harmonic filter, we have 0.75, that's the average between 99% and 99.5%. And then we add up the plus 0.8% for these two components, diodes, and this inductor 1.55% leads to 98.45% efficiency. And simple harmonic filter, depending on if they use the RC circuit or what kind of internal setup they have, they can reach up to 2.85% losses, means 97.2% efficiency. So if you look at these diagrams, you could say, okay, this looks quite, they all have quite high efficiency, which is basically true. But this small difference in efficiency can be quite a lot of energy. So if we compare the RHF topology with the active front-end technology, then we have an efficiency delta of 1.45. And if we assume we have a drive running 24/7, 365 days a year, and we pay 15 cents per kilowatt hour, that means that every year we waste $4,200 for a more expensive solution that was more expensive in the beginning and also creating more power losses. So that is the reason why I definitely never recommend to use active front-end technology for harmonic mitigation. It may be in future when we have the tree-level design of active front-end, then it might be a different point of view. But at the moment, I would never use active front-end as a harmonic solution, because you pay 3 times. You pay, first of all, you pay during the installation, your active front-end solution will be more expensive. Then you will pay again when you pay for the power losses of this technology. And then you will pay a third time because the design of a passive filter is made for 15 years. So you could replace, after 7 or 8 years, you could replace the standard 6-pulse drive with a new one, with a newer fancy design, whatever. And the active front end would also have a lifetime, maybe 8 to 9 years. So you would have to replace the drives, but you could still leave the passive filter on. Maybe you could do some tests to make sure that it will reach for another 8 years, but the design is made for 15 to 20 years. It's passive components, so it will last for a very long time. Okay. So the next advantage of the 2-stage design filter is actually the DC bus voltage. So a very common argument against the passive harmonic filter will be you have a DC voltage drop because of the impedance inside the filter or the inductance inside the filter. First of all, that's not completely untrue, but due to the 2-level design, we get a voltage boost in the beginning or in the earlier stage. So that means at 100% load, we can still have 100% DC bus voltage. So we don't have to make any derating of the drive when we use the REVCON design harmonic filter. That gives you quite a large benefit because these calculations, despite the fact that they are quite annoying, can be quite difficult and will be, you will have to get a lot of information from the customer to make these kind of calculations for the DC voltage drop. And that's not necessary, at least not for 100%. As you can see, we get 4% voltage drop at 150% load, but still that's a lot more than what we see on other competitors. And this is not the worst type competitor. There are significantly worse DC voltage drops. Okay, so that was a quick one. And the last one, not least, is the quality of a harmonic filter can be of significantly difference. I'm not saying that REVCON is the only one that can produce quality, but I would give you 2 ideas of what is essential when you buy a harmonic filter in terms of quality. If you have a big power rating, I would ask for individual full load testing, and they should have it for every harmonic filter, at least above a certain size. We do it for any size, even for the smaller ones. But especially if you have a big one, you want to be sure that it really works when you ship it around the world, and then you make a huge effort on installation, and then you don't want to see the problems that could have been detected from the factory. Then you should have high quality terminals with defined connection torque. Why is this so essential? Because a lot of filter gets damaged during setup because you connect your wiring directly to the choke. And when you connect to the choke, you will put on your tools, and if you put too much torque on it, you might bend the connection terminals, which come directly out of the choke. So that can give you some kind of problems on site. And with a defined connection torque and a high quality terminals, you will not face these kind of issues. So in worst case, if you don't know how much torque and someone is too strong for this application, you might in worst case have a damaged terminal, but you don't damage the filter itself. So that is the 2 points that I think it's essential. And maybe also the reliable thermal protection of the unit. So if it gets overloaded, somehow you have to make sure that the unit protect itself and not get overheated and in worst case even burn. Okay, so a passive filter is not a passive filter. There are some really significant differences in performance, in efficiency, and in drive performance based on the DC bus level inside the drive, and also on the quality, of course. So not only about the made in Germany or whatever. I think there are others that are able to produce good quality, but especially in terms of terminals, thermal protection, these kind of things are essential. Okay, so last chapter for today, hybrid harmonic filter and hybrid solutions. And that's what I meant to mention it earlier. I want to highlight this topic because people keep asking me, what is the best harmonic solution? Is it passive? Is it active? And half of the population on this world will say it's passive. The other ones say it's active. Or to be fair, most of people don't care about harmonics, but those who care about this topic, many of them are different opinion. And as a matter of fact, there is no best solution. It depends on what kind of application do you have? What is your situation? So if you have, for example, or let me start the other way around. Let me start with this picture. If you have a system where you have different applications or different topologies, different setups connected, you can make a quick estimation on the voltage, not on the voltage, on the current distortion. So if we look at this example and we say, okay, we have these kind of setups. We have one drive connected directly to the mains, one motor direct online, sorry. We have one motor with a small internal choke. We have one drive with a bigger one installed. And then we have a big drive with a passive harmonic filter. How can we estimate what will be the harmonic distortion from this system? It's quite easy, actually. We can take the power of the first one times the first harmonic distortion. Of course, we have to estimate these values because you will typically have this before you make this system. And if the system already exists, you could just measure. So this is something that you would make before you offer a customer some kind of solution. So we add up the first one times the first THDI, the second one with the second one, the third one with the third one, and the fourth power with the fourth THDI values. And then we divide all of these by the total power of the application, by all of these powers. And then we get a THDI input. This is what we see here. This is not the correct way to calculate this because there are some other things to consider. There's also a phase angle of the individual harmonics and a lot of other things to consider. But basically, you can use this as a first estimation because this value will always be bigger than the true values. So I have made this calculation with the true values up here, and I made the same calculation with the Danfoss harmonic calculation software, and the result was 11.2, and I calculated 12.8. So we are at least more or less in the same area. It's not an exact science. It's not scientifically correct calculation of this, but it is a first way to give you a quick estimation of what kind of result can I expect from the mains. And I think in many, many cases, this will be more than enough to decide, do I need any harmonic mitigation? Do I need any further equipment, or in worst case, or actually even to size a passive harmonic filter or an active harmonic filter, this can be done with these simplified calculations. Okay, so this is basically what we do when we set up offers for systems. So we play the game and we play some different setups. In this setup, the first inquiry from the customer was, please, we want to have passive harmonic filter on every individual drive. That was the requirement from the customer. And so we offered passive harmonic filter for every individual drive, of course. But this means 36 small passive harmonic filter for 7.5 kilowatt motors, 0.75 kilowatt motors. Then we have 32 passive harmonic filter for 3 kilowatts. So almost 70 passive harmonic filter for a very small amount of energy. And then we had 104 different size drives with a lot of different passive harmonic filters. So we suggested, and then first of all, the customer came to us and said, what about active? Can we use active for this solution? And first of all, this is 100% of the cost. Obviously, it was not 100 euros, but this is just to identify this was 100% of the cost. This was the benchmark that they gave to us. And we gave them two different options. The first one was active filtering for everything. We made the same calculation of the THDI. We got the result of 36%. And to reduce this down to 5%, we need to add 10 active harmonic filter, which result in 21% higher cost compared to passive solution. So we offer them a third solution, which is a lot more cost efficient and also technical superior to all the other solutions. We just ignore the small ones. We put some passive harmonic filter on the big drives, and then we get a quite good THDI. And then we only did the fine tuning with an active harmonic filter to get it down to 3% again. So this result was about the same as the passive harmonic filter. It's actually better than the passive harmonic filter, but the costs were reduced by 14%, which was in this project quite a lot of amount of energy. You see 104 passive filters, 1 active filter. So you can imagine what will be the cost of this project. So really relevant cost just by choosing a better, different solution, or a different and maybe unusual solution that people not yet are used to. But this is technically the best way to handle it, because you do the hard work with a passive harmonic filter and then you do the fine tuning with an active solution. And that gets you the best from two different technologies. And that is the benefit of this. Okay, so what is the best harmonic solution? All harmonic solutions have their advantages and disadvantages. Pure passive solutions, they are good when you have many big loads. Pure active solutions are good when you have many, many small drives. So there are situations where active solutions can be the superior choice. So if you have, let's say, no drive above 3 kilowatts, and they are all, or maybe even below 7 kilowatts, then an active solution will be more cost efficient than a hybrid solution, and also more efficient than pure passive solution. So for big load, passive is the best choice. And with big, I mean anything about 15 to 20 kilowatts somewhere. We need to find a balance, and that's something we are very happy to help you with. So come to us. We have some calculations tool where we find the balance of the cost when we use hybrid systems. And of course, we have active front end, which are also good for applications where you have region power. These kind of applications can benefit from the active front end technology. Okay. So the next part is an open discussion. I'm not sure, there were not many questions today. I'm always glad to answer questions. So if you have anything on your mind, anything that is open, I'm really glad to answer that questions. But of course, it's not mandatory. If you feel any of your questions were already answered, I will tell you a little bit of the active filter. But don't hesitate to write any question into the Q&A or raise your hand if you want to say something. I can just unmute you anytime. Just let me know. In the meantime, I will continue to explain a little bit of active harmonic filter. I mentioned it in some earlier slides that we will have some significant differences in RHF active topologies internally. So when I speak about system efficiency above 98%, 98.5 I think was the efficiency of the active solution, then I speak about a 3-level design. 3-level design means that we have 2 IGBTs in line with a lower voltage threshold, which is a huge benefit in terms of losses. So we can have a switching frequency in this setup up to 20 kilohertz. And at the same time, our power losses will be less than half of those from a 2-level design. That's the benefit of the 3-level topology. And that's some brands already have this topology on the market. Some are still keeping on with the 2-level design, which makes the whole solution bigger and more expensive. But nevertheless, I think this is something that is not unique REVCON technology. We have a good setup. We have put some efforts in the lifetime expectancy of the product. So for example, for a 100 amp unit, we use a 300 amp IGBT module inside, which is one of the reasons why the design on long term is very good and will be a long-lasting design. Okay, so I just see we have Lane has some question. Do you want me to put you on mute? Do you have any question? Just raise your hand maybe, or give me some maybe sign in the chat. Okay, so we have a question. I have a customer which have a great load with laser cutters and the capacitor banks is blowing the bottles. So the capacitor bank is overloaded. Is that correct? And the cables are burning? Okay. Do you have any information about these applications, about the input current? I would expect that the laser cutter, they have typically a DC input, so they will have a huge harmonic distortion. So I'm not sure if this is pure harmonic problems, but these problems that you described, burning cables, capacitor bank is blowing up, I would expect that these problems can be very, very much related to harmonic problems. So at least I would make a measurement on this equipment and see what is the voltage distortion. So you need to find someone who can make this in your area. Which area are you from? Okay, so which you are not able to do the analysis yourself, which is fully okay. If you could let me know which area you are in, then I can check if I have someone. We work with a lot of partners worldwide. Maybe I have someone that could give you a quick call and set up something to make the analysis. Colombia, okay. So just send me your email and I have someone in Colombia who could take care of this. Okay, Lane, do you mind to copy your email address into the chat? You can send it as a personal, if you don't want anyone to see it. The problem is I can't save the Q&A file because I can't copy the content. So if you could send it in the Zoom chat, that would help me a lot. Or if you can send it as an email or on LinkedIn, anything is fine. Perfect. Thank you very much. Okay, so I will get you in contact with someone who could do the quality, power quality analysis, and they will recommend you to maybe install an active filter or passive or whatever they think it's suitable for this kind of customer. Okay, before we finish, I would like to introduce our latest design of active filter, which is a very special design. It's an RHF 15 amp, so it's the smallest design on the market at the moment. It's a special design because we use silicon carbide inside internally, and this means that you will have even less losses. The efficiency of this kind of unit is 98% based on the line current it takes. So if you use this in a system efficiency, it get up to 99.4% if we design it for 30% reduction. And that's unique in this power area. No other drive are even close to this efficient, or no other harmonic solution is close to this silicon carbide solution. As a small benefit, it's switching with 60 kilohertz, which means you cannot hear it anymore. So it's completely noiseless. You can solve reactive current harmonics, unbalanced, as with any active harmonic filter, to be fair. But the main benefit that you will get from this kind of high switching device is that the accuracy of the elimination of harmonics is much more accurate. So if we look at very strong distorted loads, for example, EC motors, remember in the beginning of this seminar, I told you something about a slim DC bus where you have the higher harmonics. All these kind of drives and other loads and EC motors, they have quite high distorted or higher order harmonics. And also in part load, they can be quite high distortion as well. So we can reduce it up from 90% down to 7, or if we get from 35 strictly or significantly below 5%. So for EC motors and these kind of fan applications, this product is very unique at the moment. So that's the latest news from REVCON we introduced on the SPS in Germany this year. The next design will be a 55 amp, will come this summer. Will also be based on silicon carbide. So I'm really looking forward to introduce this to you. And I guess maybe a little bit delayed based on the situation at the moment, but I hope that it will be released at least in the late summer, maybe earlier. We will see. Okay, so as I mentioned it earlier, we work with almost all drive brands on the market today. So we have test references. We have we actually do a lot of brand labeling of our products. So even though REVCON was maybe not very well known to you in the past, you will notice that our products are quite famous in the end. So we work with a lot of big drive manufacturers. Okay, so I can't see any further questions. I hope you enjoyed the seminar. I would like to thank you for your attention, and I really hope that you all stay safe and you and your families will stay safe and healthy over this difficult period of time, and stay home if you can. And thank you very much for spending your time with this harmonic topic today. Thank you.